Okay, let's go ahead and start part two of our derivative as a function. I've already explained kind of how I feel about this section in the book. I apologize if part one of this video was maybe a little bit more scattered than you're used to. That's because I can't exactly share everything. The whole idea of taking derivatives and how they impact the domain, taking derivatives and how they relate to continuity, can't be exhaustively explained with the knowledge base that you have right now, and therefore it's more like they're talking points as we move forward. And so I kind of hesitant. They need to be introduced at some point, and I'm fine with introducing them right now. But that was kind of why I seemed like I was stopping short of saying everything, because I'm trying to remind myself exactly where you are in terms of your knowledge level and stuff like that, because you're not quite there in terms of being able to fully appreciate it yet. We are, however, in this particular video going to get to some things that are a little bit more concrete, because as I was saying and emphasizing during part of the last lecture, the function is described in terms of its slope by the derivative function. The derivative function has a role to play vis-a-vis the original function. Okay, so if I'm given something like this, and I am asked to draw the derivative function on the same axes, okay, I need to know exactly what the derivative function says. The derivative function describes the slope. So the derivative function derives the slope. So wherever this has a positive slope, and I see the fact that it has a positive slope, and it looks like from negative infinity up to 0, where this has a positive slope, the derivative function needs to have positive outputs. Okay? Now notice how this is relatively steep right here, and it gets flatter. And I'm going to try to do this in pink highlighter so you can see the different graphs. Okay. See, this gets steep right here, but then it gets a little bit flatter. So it's flat, 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 steep, 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 steep. But right here it starts to level off just a little bit and actually winds up having a slope of 0 right here at the very peak. Okay. So it's close to 0 slope, steeper, and then very quickly comes back to a 0. Well, what does that look like? Okay, now I'm not going to do it exactly in terms of the outputs, but you have a 0 slope as you're coming here. 0, it's close to 0, and then it starts to increase. Okay, but then at some point right about here it starts to decrease again and goes quickly to 0. And then, of course, something similar occurs, but sort of in reverse over here. Okay? And the derivative function looks something like that. Now, you may not understand how I was able to do that so quickly. Well, first of all, I know what this function is, and I know what its derivative is, so that kind of helps, right? But you need to be able to look at this and say, okay, positive slope, so minimally positive, much more aggressively positive, and quickly goes back to minimally positive to 0. That's why the outputs mirror the change in slope on the original function. So as this gets steeper, this gets higher. As this starts to quickly flatten out, starting, I don't know, right about here, right? As this starts to flatten out, this turns around and heads back towards 0, okay? Now, this is flat right here, and as I move from 0 towards in the positive x direction, this starts at 0, but starts to get more and more and more steep in a negative direction. Because this starts to get more and more steep in a negative direction, this starts to get more and more negative in its output. But then it starts to level off, right? You see it's sort of decreasing faster and faster, and then it goes, oh, I'm going to decrease slower. As this starts to decrease slower, this starts to have less and less aggressively negative outputs. Does that make sense? And if you just want to look at it, go, okay, well that's, let's do tangent lines. That's not very steep. Okay, it's a little bit steeper. Okay, that's steep. Okay, that's not very steep. And so, 1/10 1/2, 3, 1, and then 0. And then, of course, those values are repeated in the inverse order negatively because, of course, this is an even function. The original is an even function. Notice that the original is an even function. Notice that the derivative is odd. I wonder if there's anything to that. Okay, let's go ahead and move on to this one. Okay, let's go ahead and get rid of the one underneath because you can kind of see it. Okay, now let's go ahead and do the derivative of this one. Now here's the thing. Where this has negative slope, my derivative should have negative outputs, okay? So let's figure out where exactly. It looks like right here is where it becomes 0 slope, and that's the dividing line between negative slope and positive slope. So let's cheat a little bit, and let's sort of draw just a dividing line right there. I know on this interval over here, f prime, meaning the outputs are going to be less than 0. Now, I notice that here, again, it stops being positive slope and starts being negative again. So let's draw another one right here. And I notice that on this interval, f prime is positive. And then, of course, over here, f prime is negative. So I know that slope is negative, slope is positive, slope is negative. So the derivative function is going to have negative outputs, positive outputs, negative outputs. Okay? So what should it look like? Well, what is the slope? What does the slope look like right here? Okay, let's draw sort of an approximate tangent line and sort of go, okay, well that looks like the tangent line through there. Can you approximate that? Well, it almost looks like it's about, I don't know, slope of maybe 2.5. Okay, so let's actually use that value. We don't have to, but we can. So if we have 2.5, if the slope right there is 2.5, that's as steep as it's going to get, right? Because it's starting out at 0 and it's getting steeper as it moves. Getting steeper as it moves towards that origin point, and then it's flattening out again as it goes to here. Okay, so I know that this portion kind of looks like that, right? Now, while this is negative right here in its slope, it's not very aggressively negative, is it? So it's probably going to kind of do this number, and it almost looks like it's going to start curving back and flattening out. So it almost kind of looks like that. Now, that's not perfect, okay? But all I'm doing is I'm trying to relate the numerical positive and negative, and of course at some point you want to start to take into account the general magnitude of it as well. The positiveness or negativeness of the slope of the original tells us the positiveness or negativeness of the output of the derivative. Okay, let's go ahead and do a third example. Okay, and of course I hope you remember, or maybe have picked up on it at this point, you remember that a cubic, which is what this kind of looks like, and since I'm the one who actually created this graph, I will spoil the surprise. This is a cubic. A cubic has a derivative, which of course is going to be quadratic. Now, the slope changes here from positive to negative, right? Positive slope turns into negative slope. And then here goes from negative slope to positive slope. So those are going to be sort of how we're going to divide up the domain such that we can actually talk about it. Now, if this has negative slope here, it's going to have negative output here, right? Where there's a 0 slope, we're going to have 0. And basically, it looks like that. Which it should, right? If this was a cubic, and of course this is a cubic with a positive leading coefficient, you can tell from the end behavior. If it's a cubic with a positive leading coefficient, its derivative should be a quadratic with a positive leading coefficient. And that sort of common sense understanding actually plays out here. Now, in your book, there were actually a couple of other things that I want to get to after we get to this one right here. I've already told you that the derivative of sine is cosine, okay? And notice where sine, can you see that little cursor right there? I'm right above the blue graph, right above pi over 2. Where the sine graph goes and has a 0 slope and changes from positive slope to negative slope, the cosine graph, which is the derivative, has a 0 output value and goes from positive to negative outputs, okay? And you can go ahead and actually look at it for yourself. Go ahead and pause the video if you want. Just go ahead and look. Cosine right here is at its absolute minimum right here, because the negative slope of sine is basically maximized right here, okay? So that's as negative, that's as aggressively negative as the slope is going to get for sine. So that's as aggressively negative as the outputs are going to get for cosine. At that point, sine starts to flatten out again, and therefore the cosine outputs gravitate back towards 0. And of course, they become 0 the next time that sine has a slope of 0. Now, let's go ahead and move on to this particular question that was asked in your book. This was number 43. Now, which one of these is the original function? Okay, well, for lack of a better place to start, let's start with A. Okay? Now, notice that this has a positive slope right here up until right about here. Okay? It has a positive slope. Now, is either B or C give us, does its shape in terms of its outputs describe the slope of this graph? So this starts out moderately positive, gets a little bit steeper, and then levels back out and becomes moderately positive before it goes to 0. Kind of like the outputs of B. Look at this green graph. Moderate in terms of its outputs, more aggressive in terms of its outputs, right at the same time that A gets steeper. B has higher outputs the moment that A is at its steepest. And the moment that A starts to flatten out, B's outputs start to go towards 0. And the moment it looks like A has a horizontal tangent line or a slope of 0, B is 0. And then we see A start to have a moderately negative slope, and therefore B has moderately negative outputs. Okay, so we know that at least B is the derivative of A. So, but C, it could be that C is the original, okay? So let's actually go ahead and look. Let's at least start thinking about, okay, I know A has a derivative which is B. Let's sort of set up a hypothesis. Let's hypothesize that B has a derivative that's C, and let's see if it fits, okay? So we have a positive slope here for B, and the moment that B has a 0 slope, C has a 0 output. B has a negative slope on the same interval that C has negative outputs. And as B starts to level off and starts to get nearer a slope of 0, even though it's sort of 0 coming from the negative side, C is coming at 0 from the negative side in terms of its outputs, okay? So A is F, B is F prime, and C is F double prime, okay? Now, we could go on and on and on and on and on about this, but I found that the best way to do this is there is basically a matching game where you basically print out these cards, you print out these PDFs, you cut them up, you sort of shuffle them all up, and then you practice matching them. And there are 3 or 4 different varieties of this game, and I'm going to try and find as many as I can and link them up to the blog so that you can go chase them down. But I highly, highly, highly recommend doing those matching card games. That's one of those things that my kids from last year, they actually asked to do that activity again during AP review in late April, because they found it so helpful the first time around, okay? You may even want to ask your teacher if she's willing to spend a day letting you do that. But if she doesn't, or if you don't want to ask, I highly recommend you doing it on your own. And the PDFs that have those cards come with an answer key. Don't cheat, don't look at the answer key. But I will post a couple of those links up to the blog, hopefully right below these videos. I hope they're helpful. I hope this video has been helpful in terms of relating the graphs of f, f prime, and f double prime, and just generally in terms of understanding how f and f prime, how a function and its derivatives necessarily have a relationship of output to slope, or in this case, slope to output, okay? Shoot me an email if you have any further questions.